record. Welcome back. I missed you guys, I guess. All right, so let's talk about the schedule. So I was happy and then despondent. Okay, so this was the first year, asterisk, where none of my teaching was impacted by a holiday or some type of natural disaster. I thought. Indeed, this class has been both affected by a natural disaster and a holiday. So I went from thinking I had one extra week to actually now being down a week over regular instruction. Okay, so Alfred just wiped out week 3. We're calling that a wash. Okay, I phase shifted the entire schedule forward, but I introduced a new sort of lecture at week 8. I was going to do something on streams and try to get an industry speaker in. So that's gone. So everything was sort of pushed forward into that. The whole schedule hasn't moved forward because I sort of unplugged something in the middle. Okay, so I unplugged something in the middle and pushed everything forward. In particular, your A1 due date has been pushed back by a week. That's already been actioned. I think that should already be on the jack, actually. Okay, but then someone else pointed out, actually, that we lose Labor Day. There is a holiday on this Monday. And I don't know what happened. I'm like coordinating 2 classes, and sometimes they make Mondays, Tuesdays when there's a holiday just to make things a little bit more confusing. But in any case, we've also lost week 10. So what I'm going to do is file IO is kind of boring anyways. Like who cares? Like once I get IO, like file IO is just like, guess what? I'm pointing at the IO buffer, not the keyboard. So like who cares about file IO? It's just an abstraction. The problem was that's like maybe a half-hour lecture. It wasn't a full-fledged lecture. So in order to, because I'm not technically supposed to teach you anything new in week 13. So technically I'm introducing parsing week 12 and we'll finish at week 13. That being said, I've never put a parsing question on the exam. I only put a parsing question on the assessment, and the assessment's going to be due at the end of that week. So I'm sure you'll all be able to do the parsing question in that week. Right? You may be stressed, but it's easy. It will be easy. The parsing question that's sort of the point of getting to parsing. Parsing in Haskell is so elegant that once I give you a parsing question to do, there's nothing to do. Like the whole point of the assessment was, this is all I have to do to write a parser, and the answer is yeah, which is also why I don't test you on it, because it all boils down to working with grammars. The other thing I'd like to point out about this schedule is the assessment coverage. I have a lot of people complaining that I haven't taught the stuff that's required to do the assessment. And yeah, that's true. So I've actually, in this column, you can see that like we still need to do week 4 and week 5 in order for you to have the comprehensive information to do the assessment. The problem is I can't wait to this point to then give you the assessment and ask for it to be due next week. Nor am I allowed to give you more than 4. Did you know that I'm limited to assessing you guys 4 times, including the exam? I'd much rather give you fortnightly homework, right? Where I can say, I've taught you something, now do something. I've taught you. When I went to uni, there was homework due at the end of every week. That's just what it was. The first time I tried to do that for this class, there was a revolution, right? Okay, so I have to sort of deploy assessments so that parts of them you can't do. So next assessment, I'm going to try to make it more clear which questions you should be doing at which time. I think that's sort of like on me. I just thought it would sort of be intuitively clear that you can't do the types question before we did the types lecture, but I'll try to make it maybe more obvious than that for the next one. How is it going otherwise? Like you should have been able to do the lambda calculus stuff should be done at this point. Like you've had more than enough time to execute that. Don't feel like you have to do the hard work, by the way. Like it's just 2 points. And then the other hard on the principal types one isn't even that hard, but you should. Okay, so there's an auto grader up, 2 of them. There's a practice auto grader, like the grade scope. So if you've never utilized a grade scope at this university, you should for sure utilize that practice grade scope. We want you to implement the identity function in factorial. It's easy. It's just to sort of get accustomed to the interface, right? If you don't see green check marks, you're going to get 0. Right? If you see something like compile error, that's a your fault problem, right? I got lots of emails after people get compile errors to say, oh, we thought that was a grade scope problem. No, you have to see green check marks to get a non-zero grade. So give that some practice. Any other concerns before we just move on? Okay, so let's just get back into the course. I hope you enjoyed your impromptu break. You're going to be getting 2 more impromptu breaks in this class. Oh, that's not what I want. Okay. Just to make chat, you can see my slides. Yeah. Okay. Yes. Cool. Okay. Types and pattern matching. So this is going to be an important lecture because Haskell is a strongly typed system. Like it's actually implemented a type lambda calculus, which is something that we haven't talked about. But this is really going to limit the amount of functions we're able to write. So what we're going to talk about today is like what types are, what data are, and what classes are. So just from a very high level, we create data and we bundle data into collections that are called types. And then we bundle types together into collections, and those are called classes. And that's sort of the tower that we're going to investigate today. So a type is simply a collection of data. That's it. That's like the most basic definition of a type that we can come up with, just a collection. The easiest type that we can perhaps work with in Haskell is that of the Booleans. So we can ask for info on anything in the system. And if we ask for information on the Booleans, it's going to say, I'm data defining Booleans, and I am equal to false or true. That is the type. That is me just saying I am a type. I have exactly two things that belong to me, and those things are called true and called false. The name of concrete types are capitalized. So Haskell is a case-sensitive system. Some of you who are engaging with this principal types question have seen these sort of lowercase a's. That's called an abstract type, and we're going to flesh out what the differences are. But for now, know that if you use a capital letter, if you see a capital letter in the context of typing, that means that it's a concrete type. It's exactly one thing. An abstract type like A can be anything. A concrete type like bool is one thing. So abstract versus concrete. Names of abstract types are not capitalized. You've seen them. They're things like A, B, C, T1, T2. And they only become concrete when mixed with one another. So here's the sort of syntax of a basic data declaration. So today we're going to define some custom data and sort of make a custom class, like a very basic one. So these are the constituent parts of this line. So you have bool, and this is called the type constructor. This is the thing that constructs the data in the type. False is called a data constructor. This pipe symbol is, we pronounce or, although some people pronounce it as and. True is another data constructor, and true and false in this context are called literal values, right? It's what is the data? Well, it's literally the string false and literally the string true. We can do more sophisticated things with types, which we'll do, where these data constructors can construct over other types. Like I can have a data constructor construct over integers or over floats, right? This is called a product type. This is the most basic type of type construction called a sum type. Okay, so as I said, data constructors can take arguments or not. That example from Booleans was the easiest type that I could possibly introduce. So here's and it's already in the system. Obviously, we need Booleans. So here's a new type that we can define. So at line 1, the first thing I'm going to do is just define a type synonym. Basically, Haskell is just going to treat now the type for string and the type name as identical. It doesn't care. This doesn't give you any sort of practical efficiency, but it does make your code more readable. And when we can make our Haskell code more readable, we should. This isn't actually even the first type synonym that we've encountered. What is another type synonym that we've already seen? Can anyone recall? I heard the answer. String. What was the string a type synonym for? List of char, right? So it's better to use string than list of char, even though both are totally equivalent, because equal means what in Haskell? Equal means equal. Okay, so I'm going to say X is a cat. What's the type of X? Pet, not cat, right? So pet is a type, and that type has two data in it. A cat, that's just a literal, and then many dogs that have names. Right, so you can have one dog for each name. So this is the prototypical example because cats don't come when you call them. So what's the point of giving a name? Right, this is why you see this. Okay, so some questions here. If I say now Y is a dog Bluey, right? This is why it's called the data constructor. I'm here using dog to construct some type of data that belongs in this type. What's the type of Y? Pet, not dog. It's a pet, right? Dog was its data constructor. Cat's also a data constructor. It's just constructing over nothing. It doesn't take any input. It's like a constant. What's the type of this? If I put dog Bluey, dog bingo, and cat in a list and ask for that type, what do you suppose it will spit back? It's a list of pet. How's Haskell doing this? How did it know what these types were? Isn't this weird? Don't we normally have to tell the programming language what something is? Huh? Yeah, but I'm not saying X is a type pet. It's inferring it is what I'm trying to get out of you. Haskell has a mechanism for actually deducing what the type of something is. This is not the same in every other programming language. I can't fathom other programming languages that are non-functional that have type inference engines, right? So this is already quite special that I'm just dumping something into variables and it already knows what they are. Okay, that's important. If I put dog Bluey in to the system, and I actually want to get the name out, there's only one way of doing that, and that's by doing pattern matching. The good news is any data that you define out of the box will have pattern matching. What did I say the functional paradigm is effectively trying to simulate? A rewrite system, right? So in a rewrite system, what you want to be able to do is delineate symbols and say, I want to replace these symbols with these other symbols, right? So some way of conceptualizing data is me just saying, here's a bunch of new symbols that I want to add to our rewrite system. Okay, so this is how we can pattern match out. I'm saying I have a dog of Bluey, and that's equal to dog of name, and this is going to be a variable. And what this is going to do then into name is extract that string Bluey. Okay, so one of the issues with Haskell or functional programming in general is that a lot of the time we are decorating, we're putting things in containers like this. This dog is like a container. And we can get a lot of pollution. So a lot of your exorcism problems are going to have to now deal with some of these containers, particularly the maybe data type. And you're going to feel frustrated pulling things out using these types of pattern matching. But it's only because I want you to struggle with the inelegance of that, so that when I introduce the tools that are going to make that elegant again, you'll be able to appreciate it. Okay, so just keep this in mind. Things are going to get a little bit cumbersome, but then we're going to simplify it away, right? That's sort of the philosophy here. We're trying to build up patterns, and then we're going to notice like larger patterns over the patterns that we're discovering, and then replace those until we're going to have like one awesome pattern at the end called the monad. Okay, so what happens if I say, I'm going to put dog Bluey into a variable called dog, and then I'm going to do something like this. I'm only putting this here because this looks kind of strange. Like the fact that dog is like two things really is like hidden behind the fact that it's been put into a variable, right? But this is still going to work. If dog is a dog named Bluey, then if I say dog name equals dog, I'm going to be extracting that Bluey. What happens if I just want to type dog into the REPL? What happens if I'm going to hit enter here? Well, we've already deduced that Haskell knows what this is type. It knows dog has type pet, right? So clearly Haskell's a little bit clever. But what have we told it about that data type? Yes, sir. Well, what I've written is all that's there. So have I instructed Haskell about how to show this data type? It's like, I don't know how to display this. You haven't told me how to display it. Right, so you're not going to get show out of the box. You can put this deriving show afterwards. And what this is going to do, it's going to instruct Haskell to do the most obvious thing in terms of showing the data. What do you think is the most obvious thing to do when showing data? Whatever I typed in, just spit that back at me. That's a valid text representation of the data. It may not be the best way of representing it. There may be other ways, but it is an obvious way. Yes, sir. Just leave object-oriented programming out of here. Okay. I don't want to mix metaphors. It's just going to make things confusing. Let's just treat this as a brand new programming language. So the second half of this lecture is going to talk about type classes. And the real statement here is that I'm saying, no, I can't say it yet because I need all the language from the second lecture in order to say something meaningful. So let's just put a pin in that, and you can re-ask your question. But in any case, just saying deriving show is going to instruct Haskell, okay, just use like the obvious print function in order to show this data. Although you may want to do different things, right? We can always grab that later. Okay, so not all data can be displayed easily. Like suppose I created some data for like holding graphs, or like matrices that are like million by million dimensions long. Like it's not always clear that you should just print it as it was been stored. That's not always optimal to be looking at. So we may want to overwrite it with something else. Okay, so that's just sort of a basic type and basic pattern matching. So now let's talk about lists. So a list contains a variable number of objects of the same type. So we can't have mixed type lists. That's going to be important. So here are two lists. Here's X's. That's a list of integers. Well, it's a list of numbers, actually, 1, 2, 3. And here's a list of other numbers for Y's, 4, 5, and 6. The naming convention in Haskell that I sort of use in all of my programming is to pluralize anything that has an index or anything that's enumerable. So since this is a list, we say X's. So keep up with that naming convention. It's quite helpful. If I ask for the type of X, this is something important, right? So the principal types question I gave you, the principal type of a function is the most general type that Haskell can infer from something. Is one an integer? Is one a float? Is one a fractional? Is it a double? So it's all of those things. So when Haskell looks like at a number, it says, well, the most general thing this number is a number. Right? So that's why the inferred type for this list, it's saying, oh, I am a list of type A, where A is something that has to behave like a number. And this is the class constraint that we're going to talk about in the second half of the lecture. Do you think we should be able to add these things together? Yeah, I think we can add them together. That makes sense. Is something like this going to work? Why not? You have to make a more specific statement now that we're in Haskell. There is no general type which contains both numbers and characters. It's insufficient to say A is there. So what? What happens if there was a data type that had both 1 and A in it? Right? So it was close, but the most correct statement is to say, yeah, if I could come up with a union type, which there is, where I can say, take the union of the integers and the characters, this would be totally fine. But then that would be a list over that union type and not a list over either of those two things. So it's still a list of one type. So that's going to give us an error because there is no type for which both of these sort of data lie in. Okay, so a tuple is like a list, but it contains a fixed number of objects of arbitrary types, right? So we can have mixed type in tuples. So this is 1A true. So if I ask what the type of this is, what is the most general inferred type of this? What is in position 1? Something that behaves like a number. Okay, so we'll say that's a number. What's in the position 2? That's a character. There can only be one thing, a character. What's in the last position? Ooh, we just built that actually. So cool. So this is going to be a tuple. In its first position, it has something that behaves like a number. Second position, something that behaves like something that is a character. And in its last position, a Boolean. Yes?
How many types in the syntax that was given in line 3, where rather than just having num A by itself, we can have like num A car being bool C and use that in the pairs?
Well, car and bool aren't class constraints. Char and bool are types. This is a class constraint. This is saying you are an abstract type A that belongs to the number. Stop asking class questions until the second part. It will all make sense. I promise you. Right? Let's just focus on the stuff to the right of the arrow. But to placate your curiosity, this is basically saying there is a class of things that are numbers, and A is an instance of that. I'm demanding that A is an instance of the number class. But character is just character, bool is just bool. Okay. Sorry about the lapel mic. The clip is gone, so it's all bouncing around. Okay, so here's another tuple. It's the same. Can we add these two things together? Let's try to reason this out, right? So it's a fixed number of objects, so this can't be concatenation. So like the only other option would be like piecewise addition, and that seems kind of off the table. So nah, that's an error. Okay, so no concatenation on tuples. I said everything in Haskell is a function. Also, tuples are data or types. So this actually here is a type constructor for tuples, which we can look at and investigate. So what is this? It's saying, oh, yeah, no problem. I can construct tuples for you. I'm data. The type constructor is comma, and you just give me two types, and what I'll return to you is this. This may seem like it's doing nothing, but what is a tuple? Isn't that you just sticking a comma in between two things? That's it. So do we have any type of facilities of writing functions that aren't actually doing anything but moving things around? What are those called? Commutators, right? Like we're totally at peace with just having functions that move stuff around, right? So here's the type constructor for tuples. It says, if you give me two types, fine, I'll put a comma in between for you, and then I'll give you some functionality regarding like how to read and print and in typing and stuff like that. So let's take a closer look at this. Okay, so this is the information for the type constructor for tuples. Let's look at what this type constructor actually is as a function. So what do you suppose that it needs to do as a function, if we could guess? Right? This is the function that gives you a tuple back. So what do you have to give the thing that's making tuples? Two types, right? Okay, so one of those types is probably A. One of those types is does the next thing have to be A as well? No, okay, so let's call it B. Does being B prohibit it from being A? No, it just says we may be different, but we're not necessarily different. Okay, so we take something from type A, then something from type B, and return what? A tuple of type AB. That's exactly what this says. I am a function, you give me a type and another type, and I'll construct for you that tuple. It is the data constructor. The bizarre thing is this and this are actually different, but we'll get to that. Yeah.
Practice to define the tuples, or can we just use commas?
I'm not sure actually. Let's check. Because in Python, this would be fine. I don't know. See this, I don't think this is going to work. No, but like we could do this, right? Right. So again, we have to like, this isn't a language feature. This is a function. This is a function that's returning a tuple. Like, whereas in other languages, a comma is like a language feature, or like you put it in and Haskell interprets it as something, or not Haskell, but something else. Yes, sir. It's identical in terms of like an ASCII character, but again, we're never putting a comma without context. It'll either be a comma with brackets around it or a comma with square brackets around it. So there's also like the list constructor, this, going real off topic. Okay, so as there is a tuple constructor, there's also a list constructor where I can do things like this and get lists back. So lists don't have commas. When we display them, they have commas. But Haskell's storing them like this. Lists have spines in Haskell. I swear to you, we'll get all these questions are very good, but you're reaching very far ahead in the course curriculum. Yes, sir. Yeah.
Type brackets only.
Why can you do type brackets only?
Without anything inside the
Why can I not, or can I?
bracket.
I believe that would be the empty tuple. Yeah. Or I'm not sure actually. Yes. Backtick. Well, like probably, yeah. Backtick the comma. Yeah, it works as a prefix. So yeah, we can put it to postfix. Okay, but we can do all of the things that we have been able to do up to this point and we'll continue being able to do. Anyways, I could construct tuples. I didn't expect this to initiate such an interesting debate. But we're going to get 1A from this tuple constructor. What is this function going to give? I can partially evaluate this tuple constructor at 1. Yeah, so what is the interpretation of F? What does it do? Yeah, give me an element, and I'll put that in the second part of a tuple whose first part is the number 1. Something like that. So again, like even our type constructors are going to be functions, and thereby will satisfy all of the funkiness that the functions have been doing up until this point. Okay, this is something this is going to be interesting. Write two functions, first and second, that return first and second value from a tuple. So note, lowercase characters refer to abstract data types, capital ones refer to concrete types, but that's not the note that I really care about. Tuples don't provide indexing. Not that I hate indexing, It's just tuples don't have indexing defined on them. There is no index on tuples. How do I get the first element out? Pattern matching. Pattern matching is the only thing that data has as its natural state. So how can I then write these pattern matches? Because it's interesting, right? To note that if I were to ask you to do this, I'm sure many would start asking for an index operation in order to do this. Okay, so module sandbox. Where? Okay, so first, let's just put a typing information here. So what am I trying to do? I want to return the first element of a tuple. So what is the type? All right, so I need to type a tuple. I don't know what's in its first position. I don't know what's in its second position. So I'm just going to say there it's abstract. I don't know. I don't really care. What am I returning? A, right? Because the thing in its first position. Okay, so now what do I type? First of, and I guess this is X's. Pattern matching. Okay, so I have to pattern match out of this. How do all tuples look like? Sure, I'm going to say X comma Y, right? So remember, we did pattern matching. I said if we said dog name equals dog Bluey, oh, that's not going to work because I don't have this data. Okay, but if I have X, Y is equal to 1, 2. Whereas in some languages, this is called tuple unpacking. In this language, this is called pattern matching, right? It's saying, well, if everything has to be equal in this expression, then I have to match everything in the interior and make it equal. Okay, so this should be equal to X, yeah? All right, let's just give it a try. Oh, wait, load sandbox. And then I can say first of this tuple, boom. Hey, we did it. Okay, so other things, if you're compiling or if you're running Haskell with WOL, you're maybe getting a lot of warnings. This would generate a warning. Does anyone know what warning this would generate? You have defined a variable and not used it. That's kind of weird. Oh, it's this one I don't want to use. Well, I don't care. I'm not going to use it. So that's what the underscore is used for in Haskell. This is sort of just basically saying, I want an unnamed variable, right? Shut up. Compiler warnings. I'm aware. I don't want to use this. So it's something like this. So how would second look like then? Well, I think that's easy. We just take this, we do this, and instead return B. This should be like this. This should be like Y. And then we get first and second. Yeah.
For any length tuple or just tuple?
This is only going to work for length 2 tuples.
Possible to make one for variable size tuple.
Yes.
What would the type look like?
It would be a functor.
We haven't got that.
We haven't got there yet. Do you see a theme emerging in this class? Trust the process, please. Just trust us. Like we're going to get to the complicated things, but we have to do some of the easy stuff. I love these questions, and I would love to be able to like tackle that right now, but I gotta stay structured. Okay. But these are all excellent. This is all evidence that you guys have been studying, and because you can't ask these type of questions without onboarding like good understanding. Like this means that you're understanding so far what we've been doing. So these are excellent questions. Very good class. You're also good looking and athletic. Yeah. I'm going to start rate limiting you, but go ahead. Yeah.
How many patients do you have for questions that are too far into the future?
So my daughter was up at 3 a.m. screaming her head off because she's simultaneously teething and sick, right? So I've maybe had 2.5 hours of sleep last night. So you can estimate the amount that my patient's cup is full or not full. I don't think it will require that much thought. Anyways, okay, so we've defined this first function. We've defined a second function. Pattern matching is going to be the name of the game because you won't necessarily have access to tool sets that you're used to, like indexing, right? So the first thing that you should be always trying to do when defining your functions is pick up any of the patterns that are pick upable. And we'll do a little bit more. We can use tuples to evaluate functions of multiple variables in a more familiar way. So here's a function that takes a tuple that's like an integer, and returns an integer. I can define a function like this. It looks very mathematical and it works. Okay. Sometimes we in fact do define functions like this because it has like this one-to-one relationship with what we see in math, and there's utility in that. But what is really happening here? Do I really have a function that's taking two things and returning like one thing? No, I have a function that's taking one tuple and returning one integer. Okay, so this is not really a bivariate function. It's a univariate function that maps single integers to tuples of integers. It's more correct thus to write something like this, right? This was f space this tuple is equal to plus ab. This is also kind of pattern matching, right? Like this is the declarative style of programming, right? The fact that we wrote this here is sort of useful and meaningful for the other side. So again, it's more appropriate to say f1, 2, or 3. But nonetheless, because there's these two options, right? It's sometimes attractive to go from tuples into constants because it looks like math. We want to be able to convert in and out of it. Okay, so there's two forms that we have. Currying refers to the nesting of multiple functions, right? So a curried bivariate function is not really a bivariate function. It's a univariate function that goes to a univariate function that goes to an integer, right? Or that is like one thing goes to a function which goes to one thing. That's our notion of a bivariate function. That's called a curried function. Uncurrying is the process of being given one of these functions and converting it into the tuple version. So here's an uncurried version of a function, right? It takes a tuple and it returns an integer, and it's named after the logician Haskell Curry. I think he was a student or maybe a colleague of Turing. They're both working on their models at the same time. You sort of discovered that they were equivalent. That was also fairly remarkable. Uncurrying. Okay, so this is when you have a function f and you want to call it using a tuple instead of using the sort of like currying fashion. So to uncurry something, you give me a function f, which we normally, you've given me a function f, which is expecting to, I have to get my P's and Q's straight here. Yeah, f is a function which is expecting to take this tuple, but I want to uncurry it instead, so I can call it like this. Okay, so we'll walk through like this. So here is a function defined in its curried fashion, and we call it like this, right? H of 1, 2. So this means 1 goes to where? X or Y? X, and then 2 goes to Y. I like to think of H sort of eating its way across. It eats 1, and then H becomes the function 1 plus Y, and then it eats Y and becomes 3. That's how I think about it. Therefore, we can uncurry H and then call it with a tuple instead, right? Rather than the 1 and then 2 and get 3 back. That's not the overly interesting part. Can anyone tell me what the type of uncurry should be, given this sort of like small usage example? Well, we can work through this, right? So we had to give it a function h. H is defined in a curried way. So that's something like A to B to C. Then the next input has to be what? A tuple. So that's a tuple AB. And then what does it return? C, right? So to uncurry a function, you need a function that's curried, and then a tuple, and then I can give you back a output, C. Note, uncurry is included in the prelude. Curry, okay, that's to do the opposite. So now you're going to give me a function that I prefer, like the one that you're sort of calling A and then B, and converting it into one that's expecting to take tuples. Right, so here's a function h of x, y. And sort of curry, this one is more useful than the uncurry, I think. I think there's much more utility, because what's the disadvantage of having a uncurried function, the one that takes like a triplet to something? Can you partially evaluate that? No, and I like to be able to partially evaluate things. That's a good feature of this language. So to be given a function that's like uncurried and currying it is useful. Okay, so here's the uncurried function. It's expecting to take a tuple like this, and it's just going to sum that tuple. I can call it like this in its uncurried fashion and get 3, but I can also curry h and then call 1 and then call 2. And then this is going this will evaluate it in the sort of stages of evaluation. 1 will go to h, and then 2 will go to that, and we'll get 3 back. So the interesting part here is, what should the type of curry be? So let's just walk through it again. So curry takes as its first argument f. What is f? That's a function that's defined in an uncurried fashion. So that was a function that took a tuple AB to what? We don't know. C. Okay. Then we have to take something from A, so arrow A. Then we have to take something from B, arrow B, and return what? Something from C, arrow C. So I expect the type of curry to be is something that takes a tuple AB to C. That's the first position. This is a function. And then something from A, and then something from B, and then I'll give you back something from C. Okay, so we can always convert between these curried and uncurried functions if we want. I don't ever think I've ever used this really. But you should know that such a thing exists because it's often the case that mathematicians will define mathematical looking functions because it's more consistent with the literature. Yeah. So like I'm going to go through some examples of the principal types questions, but the purpose of that principal types question is for you to play with the type inference engine. Right.
That looks like bottom row is like the question and the top row is like the answer.
Kind of, yeah. Like I'll walk you through. I have some examples at the end of this where I'm going to walk you through how to do some of it because it's easier than it may seem at first glance. Okay. Okay, so again, everything in Haskell is a function. When we're building functions, what are functions if not types? So this arrow is a type constructor that constructs function. So let's look at it. So the function constructor type, this arrow type, it's this. It says, give me, I'll just put an arrow between two types. It's kind of like a decorator like that. They removed this actually in the sort of more recent versions. I'm not sure if you typed out info on this that will show this anymore. I think now it says it's in the subsystem. That's been happening a lot more recently. But in any case, it's not that informative. But again, you're just putting an arrow in between two types. It has extremely special order of operational precedence, like -1, very, very last, even after 0. And it's right associative. That's the important part about this arrow. Right associativity. You can always bracket to the right, because you're always having a function return a function. That's like everything to its right. So we'll discuss that. Okay, so this means that if I have a function foo, and like we would sort of call this a function that takes 3 integers and returns an integer, but we know it's more accurately a function that takes an integer, that returns a function that takes an integer, that returns a function that takes an integer to an integer. And that's exactly what's codified by those brackets underneath. This is an integer that returns a function. That is an integer that returns a function. So you can always you can always add or dump right brackets, and it will remain equivalent. So you're not going to get identical matches from the principal types homework to the REPL. There may be right brackets there that we've put, but if you can remove right brackets, can't remove left brackets. Okay, so if I put an arrow between bool is the data that we constructed from scratch. I'm saying this is going to construct all of the functions from bool to bool. How many functions are there from bool to bool? I hear 4. Okay, that's not a lot. So what are the 4? Everything to true, everything to false. The not function, that is true goes to false and false goes to true, and then identity function. Okay, so you can regard this arrow as kind of like a special Cartesian product that filters out all relations that aren't functions. So remember from the very first class, what was a function? Oh, well, you just give me 2 types. You construct tuples from those 2 types. Any subset of that is considered a relation, and those relations that satisfy the vertical line test are considered functions. If in addition to that, we assume that like everything your domain has to have mapping from, that is, it's a total function, you can regard sort of as this operator as just leaving behind everything that's permissible to be a function. So in this case, this would sort of represent exactly 4 things. Take your pick from any of these functions. That's one way of conceptualizing this arrow operator. Okay, so let's take a look now at like how bracketing sort of affects our interpretation of these things. So here's a function that sort of takes 3 integers and returns an integer. But again, interpreting in its curried way, it's a function that returns functions. Here's a function that maps takes 3 integers and maps to an integer. This is going to satisfy that type. Okay, I don't know why I put a 1 there. Well, just to show that it's sort of evaluated to the thing that I wanted. What is the interpretation of this? These are left brackets. So is line 6 different than line 1? Yes, right? Because those are left brackets. And we can clearly see that it should be different. What should the first argument to G be? A function. What was the first argument to F? An integer. Okay, so those brackets did change the meaning. Okay, so here's a function G, which I'm going to define, which has that type. So G has to take a function and an integer, and it has to return an integer. Well, if the first function was a function that took integer to integer, and this is something that's an integer, then what happens if I give k to foo? Becomes an integer. Okay. So we can ask for the type of this and get an integer to integer function. Okay, I'm going to move the brackets now to the middle. Is 11 the same as 6? Is 11 the same as 1? Okay, so again, these aren't brackets that we can remove. These are this is meaningful now. So what is the difference now between H and F? So what should the first argument to H be? The second argument should be a what? And the third argument should return an integer. So here I can say something like, oh, I have H, I take an integer, I take a function which takes an integer to an integer, and then I can return foo of k, right? Because I know foo takes an integer to an integer, I know k is an integer, so I know that's going to return an integer. Okay, this is sort of type level programming. This doesn't feel like we're actually doing anything, but it is in fact doing something. What about this? Same as 1. You could remove those right brackets, right? Because think about it this way. So f takes an integer and returns that function, which takes an integer and returns that function. Well, so this takes an integer and returns a function, which takes an integer and returns that function. Okay, so there's another way of defining this so that I can sort of like force Haskell to put those right associativity brackets there. But the real purpose is that there is no difference between 14 and 1. If you solve the problem for principal types and you see that you are absent right brackets, as long as they're right brackets that aren't meaningful, it doesn't matter, right? It's equal, right? So 14 and 1 are the same, but 6 and 11 aren't the same as 1. The brackets are on the left, not on the right. Any questions about that? Cool. Here are the basic types of Haskell: Booleans, true and false; characters, the single characters; strings, which are just list of characters; integers, which are fixed precision integers, probably 64-bit at this point. We don't use them. We do use these integers, which are arbitrarily long integers that helps us with our functional purity. Floats we don't talk about at all because I just don't want to deal with them ever. Double is just a float, but like double the amount of storage capacity. Does anyone know why a float's called a float? Why is it called a floating point then? Exactly, yeah. So like really like you have some memory, it's a box, you can put your number in the box and then you can sort of move the decimal around. You can float the points, right? So I wish I would float or get to the point, I'm sure you're thinking. Okay, type inference. So now this is the thing that's relevant for your principal types homework question. So the fact that Haskell has the type inference engine is one of its main features. This is one of the reasons we come to functional programming, is to obtain type inference. Often when students graduate out of this class, they come back to me saying, I wish other languages had this. This is so useful. I could give a whole class on Haskell's type inference engine. It's complicated. It's brilliant, the people who did it. I'm not going to do that. We're just going to play with it a little bit. I just want to get some appreciation for the type inference engine. So let's talk about how it works. Okay, so I'm going to define a function. It's going to take two things and add them. So what is the most generalized inferred type that Haskell can give this function? And the thing that we have to be careful about is when things are interacting with one another. This is the name of the game on your p-types question. Make the right things interact. So Haskell is going to make the right type of inference. What do we see interacting here at 1? X and Y, right? So how are they interacting? We're adding them. So what does that already mean, X and Y? There's two things already we can conclude about X and Y here. They're probably numbers. And are they different numbers? Sorry, are they different types of numbers?
Well, no, that.
Are we permitted mixed type arithmetic in Haskell? No, this isn't not Haskell, okay? So we can only add the same type. So this means that if X is type A, Y has to be type A, not type B, type A. They have to be the same type because they're interacting, right? The only things that can be added are two integers or two floats. You can't add an integer to a float. You can't convert an integer to a float. Silence. I know this is strange. You have to take an integer and make it a number, and then take that number and make it a float. That's how you have to move up the chain before you can't move across, right? So this is the typing here is different than the types that they exist in a sort of hierarchy. Okay, so if I ask for the type of f, I suspect that this is going to say, you need to give me a number type a because you're adding, and we'll soon learn that something that belongs in the number class is obligated to have an addition function. And in addition to that a being a number type, it has to be the same for both because they're interacting. Okay, so f is something that takes a numbered type a and goes from a to a to a, right? Two numbers to a number. Okay, what about this one? What's the type of f if I give it 1? A to a, right? Because 1 has what general inferred type? Number, because it's an integer, it's a float, it's a small int, it's all of them. Or it has the capacity to be all of them, I guess is what I'm trying to say. So we have to leave things as their most general form at all times. That's what Haskell's trying to do. Stay as most general as possible. So the type of 1, as we just said, is a number, right? Not an integer or anything like that. I can type cast. I can sort of say, oh, give f1 the integer. If I give f1 the integer, right, it's going to sort of partially evaluate. What will its type be then? Integer to integer. And it's now there's no constraint anymore because this is a concrete type. This is the single type integer. Because once it realized, oh, your first argument here is going to be an int. That first argument's interacting with y, so that has to be an int. So that's the inference working. So the most general inferred type of an expression, it's called its principal type. What's the principal type of this? This is f of x, y goes to the tuple x, y. Are x and y interacting? Not meaningfully. What can go in tuples? Mixed types, right? So what is the type of f? Something from A, something from B, and then I'm going to give you back a tuple AB. Can B be A? Can A be a list? Yes. Why not? Is A is what? A stand-in for a type. Is list a type? Yes. So these can be, I'm not saying it can't be a list. I'm just not saying that it must be a list. Okay, so it's tough. When you remove constraints, more things are available to you. Okay, what about this? If I say I'm going to put a 1 in the first position of f, what's the type going to be now? Yeah, something that I'm a number type, right? And I'm going to go from B to AB, right? Because it doesn't know what 1 is any number, right? So that's what it confer in this case. What's type of 1 if I cast 1 to the integer? B to integer B. Okay, what about this one? I just totally, I put a 1, an integer in, and a character in. Integer to character. I have an alarm going off. I don't know why. Okay. It's best to declare our types rather than relying on the type inference engine. We normally don't rely on the type inference engine. We usually start with the type annotation. So here's like comprehensively how you could sort of do that. The last one is the way that we really want to do it. So I can say here's a function that's just going to quadruple something that is multiplied by 4. Its type is going to be, I'm a number, A, and then I'm going to return to you that same type of number, A. I can say, oh, you're quadruple, but the thing that you return has to be an integer. What does that now induce about the input type? Has to also be an integer, right? So one way of doing a sort of type cast is to demand the output has to satisfy, some concrete type, and that will propagate through. This is the best way, and this is how we'll always do it. Okay, I'm going to say quadruple is a function that takes integers to integers, and it's defined as following. You're not allowed to change this on your homework. And every year I get chuckles. Hee hee tee hee. Of course we're not allowed to. There are types. In order to use things like equal, you have to have a type that provides it. So if I say, write me a function which counts frequencies in a list that's list type A, there'll be people who are like, I need to use equal. I'm going to put equal, and I'm going to now make that a class constraint. I'm going to change the type signature to include equality. You can't do that. You can't change our type signatures. So just be careful about that, because the type signature is also going to, it's going to be a constraint on what the type is actually going to provide for you. right? And you may not get things like you think every type should have like a quality. That type we had before, the pet type, didn't have a quality on it. Cat wasn't equal to cat, not until we tell the system that that's the case. So just be mindful of that. Okay, so I just need to teach you a few things so that you can do a little bit more homework, but we're going to flesh it out more later. So I want to finish this half of the lecture with talking about if expressions and then the maybe type, and then I'm going to solve question 1 on your homework. We'll do it together. I'll give you free 2 marks. So someone please load that up for me, so we have it ready. Okay. We don't have an if statement in Haskell. Has anyone discovered this yet? And tried using it and keep embedding them? Okay, so it's sort of clear that if we can kind of see what's an if statement, if not a function that takes 3 inputs, and on true, like if the first input is true, it returns its second input, and if its first input is false, it returns its third input. That kind of sounds like an if statement, right? So let's investigate this. Well, here's the type of if. What do you notice about its type signature? It's A to A to A. Okay, so this means that an if statement can't return an integer on one branch and a character on its other branch. An if statement can only return the same type across all of its branches in Haskell. This is why it's not called an if statement. This is called an if expression. And you really only utilize it if you want to branch and that branch is exactly split in 2. An if statement in the imperative programming paradigm is just a capacity to skip statements. That's all it does. That's not part of our model. We don't have sequencing, right? We don't have sequencing. What does it mean to skip statements then in that sequence? So no if statement, if expression. Well, but what happens if we have sort of this union type? What happens if I can say, okay, I'll take A and B and then return A union B or A or B? That's kind of flubbing it now, right? Because don't you really then have a function that takes A union B to A union B to A union B, right? You've just pushed yourself back into the first position, right? Of just returning the same type across all branches. So the if expression isn't doing what you think it's doing, or may not be doing what you may think that it's doing. I should never see if expressions embedded, surely, right? You only ever use this if you're in exactly a condition where you need to branch. Right. So it's very unusual that I'll reach for an if expression, although there are going to be some places where we're going to have to, right? So this is a warning, right? Don't reach for this, right? If you start embedding if expressions and other if expressions, stop. You're not leaning into the paradigm properly. Okay, so we can have if true, then 1 else 2, that gives you 1, the false gives you 2, but this won't type. And that's the other thing. You're going to get, it won't even compile. And you'll be scratching your head. What have I done? Okay. Pattern matching on lists. Okay. So we're going to go more in depth how lists work later, because they're quite interesting. For one, they have spines. The other thing is they're not presumed to be finite. So we're going to have some discussion about how is it possible that Haskell lists are infinitely long. But every type, every data can be pattern matched against. So if I have a list like this, 1, 2, 3, I can say this. Right? Because I sort of said earlier that this is the spine of the list. This is sort of the comma. This is going to unpack this into its head and tail. And the interesting thing here is this, I hit enter and didn't get an error. Isn't that strange? What's in Y? What's in Y's? Empty. Cool. Okay, so a singleton list is one number, and then the last thing that is attached to it is the empty list. That's how we can detect the end. What about this one? If I hit enter, this will error? No, because Haskell is a delayed language. It's a lazy evaluative language. It's not eager. So I can do this. It says there's nothing syntactically wrong with this. You're asking me to do a pattern match out of a list. I can't, there's nothing wrong so far. If I say then what is Y, then it tells me that it can't do it. So that's the other mode shift that you need to have. Haskell doesn't evaluate until it absolutely has to. It's a lazy evaluative structure, whereas C, things like most things in Python are eager evaluative. This is one of the reasons we can have streams, infinite structures, because those infinite structures don't exist until we try to traverse them, and we can never infinitely traverse them. Keep that in mind. Okay, so you can type infer with lists too. If I say f of x returns bracketed x, what is the inferred type here? Yeah, so what do we know about x? What type is it? I don't know. A. Is there any constraints on A? No, and I do. Okay, so and it goes to what? A list of what? A. Cool. So type of f is A, the list of A. So you can get Haskell now to put lists in its principal types. Okay. I hate this, but I indexed. Okay. So f of x, I'm going to return x's the thing at x's first index. What is the inferred type? No pause. Okay. So Haskell's like, oh, you're indexing. So x has to be a list. List of what? Well, A. I don't have any other information here. And then what am I returning back? Well, something from inside the list. So that's an A. Yeah. Oh, I'm very happy you asked that, because every year I have a conversation about head and tail and how we shouldn't use it, but people use it anyways. But I was so delighted about this new feature that Haskell has put in about this. Don't use this. It's unsafe. Right? I'm so happy about this. So we have head and tail, but they're partial functions. We shouldn't really be using them. It's the system now is saying this is bad coding practice. Do pattern matching instead. So do pattern matching instead. And if you don't agree with me, well, you're not agreeing with your professor and the maintainers of Haskell at this point. So you better come with your axes sharpened. Okay. One more. Okay. So how about this one? F. I'm going to try to capture this pattern and return X back. What is Haskell going to infer about this type? What is the type of F? So it says, oh, okay. So I'm asked to decompose. I'm trying to do a pattern match on a list. So I can now at this point deduce that the input coming to this function is a list. The thing on the right-hand side here is the X. Oh, that's the head of the list. So that has to be a scalar or a constant, something from inside the list. What about happens if I reverse this? I'm now going to put the X's over there. Well, now it says I can determine that the input here is going to be a list of A, and the thing I'm returning is the tail of the list, which is also a list. So that's going to be type A to A. Okay. I had some practice here. Okay, I'll do this one, and then I'll do your homework. I'll give you free 2 marks. Okay. So let's just pull this one out, and I'll show how it's actually not that bad. And I'll show you why we had to make some restrictions. Okay. So first of all, the reason that you're not allowed to write this type in your homework code is for this reason. I can just write this, and like this type is trivially going to have the type that. Okay? You're not letting, if you put in this line 3, Haskell's type inference engine isn't permitted to run. You are telling it what the type is supposed to be interpreted as. Okay. Whereas if I remove this and now ask for the type, it's like, hey, that's literally nothing. This is like, there's nothing to do here. Okay. So that's why you're prohibited from writing this. It trivializes the problem. So the question is, can you define something here that when I ask Haskell what its type is, like what it is inferred, it should be that. And it's not that bad. I think now that we've done the types lecture, we could now start engaging with the types question. So this is a function type A. What's its input? Let's start from the top. We're always top in, not bottom out. Okay, so it's a tuple of what? It is a function, specifically one that goes from A to B. So I'll type it like this. It's not meaningful. I can put any name there, but this is going to be helpful. What's in the second position here? A, okay. How can I get a B now? I need this to be B. What have to interact with one another for me to get a B? Well, I have a function that takes A to B. Do I have A? So why don't I just give the function that takes A to B A? And let's see what this is inferred. I see a hand raised. Yeah. Maybe type and I'll read it. Yeah. Okay. So the fact that this is T1, T2, T, it doesn't matter. You can permute those, right? All T1s can be replaced by A and all T2s can be replaced by B. right? So we're only asking that you're accurate up until changing these things. Oh, they can't see the idle. That's a good hand raise. Thank you for that. How now, chat? Yes, yes. Okay. Okay, give me the homework problem. We'll do the homework problem. What is it? Or we can just move on if you don't want free 2 marks on your homework.
Two functions. So function
Just go from left to right and tell me what character to type.
bracket
Left bracket, yeah.
A to B, comma B to C.
This is the first question?
Skip the bracket.
Yeah.
A to C. So function A.
That's the first question?
Bracket A and C. Almost. Yeah, that's
This one, bracket? I don't believe you. This is the first question? Huh? Can you guys be honest with me, or I'll just move on? This is the first question, as stated like this. I'll have a talk with Vlad. Okay, we'll see. Maybe it's not as hard as I think. A to B, B to C. Oh, that's just function composition, isn't it? Okay, so sure. Type A. Okay, so I'll just get rid of this, but sure. I'll just call this bar. Okay, so I have some function bar that takes F A to B, and I have another one that takes B to C. So I just got to make sure that, okay, we can do it. And we don't have, like, there is a function composition operator, which you don't have yet. So we won't do it that way. I'll just say, oh, fine, give me something from A, or A into something. So what should I give A? A should go to the thing that takes FA to B, and that's going to give me back what? B. What should B go to? Well, the thing that's expecting B and going to C. Oh, F. No, FAB given A gives B, NFBC. Yeah, you're right. Okay. That should be it. Oh, was that a tuple? Okay, sorry. Then I just have to make this a tuple. That's an easy change. Right, so I just want you to play with the type inference engine. Like you'll get a feel for it, and it's useful because then we'll be working with sort of more sophisticated functions. Like the whole challenge of programming in Haskell is going to get all the types to match up, right? So you've got to get used to this type inference engine. Yes, miss? Okay, so like first I delineated what the input was, right? This is a tuple. So that's why I wrote tuple. Okay. Well, this is a function that should take A to C. Isn't this a function that takes A to C?
Yeah, it doesn't say FAC.
Well, A goes to this, and this is a function which is expecting to take input from its right. And this is a function which is going to take input, this. So this takes input and returns what? Well, I know it's from this position, so this was going to return B. And once this returns B, then handing it to this is this B. And then what comes out is C. So this is a function that takes A to C. Yeah. This is a lambda calculus expression. Right? This is how I take A into something. We could do it like this too. I can say this is equal to spam, where spam of A is, I have to do this again. I want to give f of A, B, A to get a B, and then I want to give that to BC. I get a B from this, and that goes to here, and that becomes C. There we go. There we go again. Right? And because like I don't care about the fact that there's no right brackets there, because as we discussed, it's right associative. That's one of the learning objectives here is to be able to identify these as being the same. Okay, maybe we can do one more. I can see there's some hunger for this. Pick one. Huh? What about function composition? Please. Yeah. Oh, dot. We'll learn about this next week, function composition. right? How to take two functions and glue them together. This is going to be critically important, right? Because all we do in Haskell is define functions. So to be able to put them together is what defines programming in the functional paradigm. Did you want to do one more, or do you want to go to type classes? One more? Okay, pick one from here. You want me to do the most difficult one? You're going to get the... So does this one, and it's the second easiest one. Let's do the second one. If I do the hardest one, like it's... I'll give you all the answers to these too, if you want. We'll do the second one. Okay, so this one. Okay, so there's the type that we want. Let me just call this bar. Okay, so let's just scrutinize what's here. Okay. So I have a function bar, and what is it taking? Well, a tuple and something from A, right? It needs, and I need it to be equal to something, and I need it to be equal to like a tuple, and the tuple needs an A in its first position and a list of B's in its second. So I have an A, right? So here's an A. I know that type A is of type, so I'm going to put that A here. Also, let's just do this so you don't think that there's like an actual association between the names I'm typing here and those names up there. So I have an X here. Where am I going? I have an X here. I know that has to be type A. So that's going to be type A here. What I need here is some type of list Y's. And I'm just going to sort of kick that can down the road where Y's is, I don't know yet. But I know it has to be some type of list. And I know in order to force it to be a list, I'm going to have to pattern match out of something. Just putting Y's there is insufficient because that doing this pattern match is the thing that forces a list to come into being. Okay, how can I actually get a list here? I need something here that's like type B, right? That's how I extract the list. How can I get something that's type B? That's one function in here. So I have a function, right? Foo, right? So I think it was my mistake for calling that a tuple. And the function takes tuples to B. Okay, so do I have a tuple that has like, can I build a tuple AA? Yeah, I have X. X is of type A. So this XX should be of type A, right? X is of type A. So this has to be tuple type AA. If this is tuple type AA, then I can just pass it to foo and B will come out. That's what it is. Okay, and then if I save this, I should look at the type of bar. That looks right. Yeah. You just need some practice with this. Like I'm just trying to demonstrate to you that if you think about it the right way, these problems are going to take hours. Once you get a little bit of practice, you'll get quite good. And trust the process. It's necessary for you to play with the type inference engine because the type system is so critically important to everything that we're doing. Like, we'll eventually give you the answers if you just prod it out of us, but that's going to be robbing you of learning. Right? So don't be too stressed about getting these marks. You'll get them. It's low hanging enough. Okay, should we move on to type classes? You guys want a 5-minute break or anything like that? Because you guys are getting kind of chatty. Okay, let's take a 5-minute break, but really 5 minutes. After I need time, I need some rest. Yeah. Yeah. Okay, hold on. How is a short question?
It's more about like ternary expressions though, the things.
Okay, let's see.
Well, we're like you said never to use them.
Let's see.
But that's exactly how I solve leap year.
That's fine.
Yeah.
I
mean, yeah.
Fine. Yeah.
I guess the
When
question.
I say never, I'm saying like, okay, I should
guess-
be more appropriate and say my preference is to do the following. Right?
Yeah, well, you see, I know about ternary expressions in like other languages, and so that's
Okay, but you're importing. This may be something that hurts you later, is what
Yeah.
I'm suggesting. So,
it's still the same type. That was
but it may hurt you. I know things that we're going to be doing later.
okay.
And if you don't trust the process, by that point, you may like the thing that you've taught yourself. Just trust me, please, right? I swear to you. Yeah.
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 Hi, Paul. First of all, if we ask questions and they are for the future, just tell us that
Yeah.
because
No
we're
problem.
curious. We actually
No,
don't know
that's
what's
no
coming up
problem.
in the
Yeah, yeah.
future. Okay, one thing you said was basically type constraints, but basically we're constrained. But one thing I've been thinking about in one of my solutions is sending the info to a helper function where I actually define a different type
Yeah, yeah,
signature and do it. Is that allowed? Because you're sort of
Yes.
avoiding the type constraint in the original signature.
Well, yes, yes, I get asked this question but it's like, of course you, like, it's going to be literally impossible to program some of the things that we ask you to do without defining more functions.
Yes.
Yes.
No,
Yeah.
but.
It will
I'm
still-
saying
as-
the way you said it in your lecture, I just thought, oh, maybe you mean that you can't actually change certain things you're setting up in the original signature, but it sounds like
No,
you
what
can.
what comes in from the user you can't change.
Oh.
So if I'm saying this function goes from A to B to C,
But you could hard code more input in the helper function.
yes, but that's already through the abstraction. I don't care about that. I'm saying I'm here. I need this specification. You implement it, right?
Okay.
But then when you implement it, that's going to have to type satisfy eventually to the thing that I'm asking for,
Yes.
right? Because it's possible that then you'll put in a where clause that actually forces the original function you're programming to have a different type
Okay.
because they interact. And as soon as two things are interacting, then they have type influence on one another. That's what I'm trying to,
I understand what
yeah.
you mean.
Because so you could be
check that.
programming something and I'm like saying, if I'm like, write me a program for determining a character frequency and you start using equal, I'm like, no, I'm not permitting you to use equal, right? That may not be available to you. So if you wrote a helper function, which is using equality, then that gets bumped up to the original. It's going to say, hey, I need to add an equality instance to the top level.
Yeah.
And I'm saying that's not what you're allowed to do,
Okay. Yeah.
right? But it won't work, right? As soon as I define a type and you try to define some helper functions that
Yeah.
violate that, Haskell simply won't run. It won't even work. But I'm saying I'm saying at that point, you're not allowed to go to the original, the thing that I gave and start adding things to it. You're free to add helper functions,
Yeah.
but they have to be typed properly.
So can I assume if I've done a helper function, I've changed something or hard coded something extra into it, and it's passing the grade scope test, it's okay?
Yes,
Okay.
yeah. As long as you don't change type signatures that we provide for you, it's fine.
Yeah.
Then it has to type. Haskell won't run. It won't compile
Yeah.
if it doesn't type. Yeah.
Thank you.
Okay. Yeah. Oh. I think you should be able to do most of those questions now after this class. Give it some thought. Yeah. Just try though. Try it. Like, you're supposed to be confused sometimes. That's deliberate. It's the sweat of learning. Yeah. I didn't have access to stuff like this when I was a student. Like, there was no discussion forums. There were no lecture recordings. There was like 1 hour I could see the professor begrudgingly per week. So, and I'm not sure I think that was better. It forced us to engage with the material or sync effectively. Yeah. No bears. Yeah, that was. I'm not sure Richard Dawkins had invented the term meme by then either. The earliest meme I remember at one point, YouTube was mostly about cats. Like, that was sort of like as meme close as we could get. And then there's the Nyan cat. Do you remember? You guys know that one? Do you guys know Maru? Okay, see, that ages me. That was like the most famous internet cat, was Maru. No, debatable. Was the cat the thing that was famous, or like the meme the thing that was famous? I'm saying the cat was the thing that was famous. Like Maru was like. Oh, it's.
She and Grumpy Cat were in the same room at one point.
But there is a grumpy cat, or is it like a category of cats?
There is a specific Grumpy
Okay.
Cat.
Yeah, see, that's the difference.
That called Grumpy Cat. They just had the most common face.
Okay, let's go. I don't want to be late because this is an important lecture. So let's get her done. Let's resume. I just have to re-onboard Bears. Coffees, I have one. Still. Can you see chat and hear me, chat? I think we're recording. Yeah, we're recording. Yes and yes. Okay. Type classes. All right, so we spent a lot of time talking about types and data. So remember, a type is a collection of data, and data have constructors. And so what we're now going to do is collect the types into things called type classes. So you can think of a type class as a collection of types that provide similar functionality. Are you familiar with what, if I say set builder notation, do you know what that is? Okay, so somehow so in mathematics, we call it set builder notation. In programming, we maybe call this list comprehension. Okay, so you can have some type of list effectively. It's like X for X in here if PX. Or in set builder notation, it's sort of like X is in this set if PX. So PX is like a predicate that sort of tells you if you belong in the category or not. That is what, technically speaking, a type class is in Haskell. It's a predicate that effectively tells you if you're in a type class or not. Okay, so to be in the numbered class, for example, you need to define things like addition, right? And once that's satisfied, then you get to belong in the numbered class, right? So most precisely, a type class is a set of functions defined over a type that says, if you define these, then you get to belong in our party, in our class effectively. So for example, to be an ordered type, you have to define less than, greater than, and equality. To be an equality type, you have to define equality. And already you can see that these type classes aren't going to be disjoint, right? There are two, everything that is going to have an order is also going to have equality. So when a type has an instance of a type class, values of the former can be used with functions of the latter. So for example, if we ask for information on bool, we're going to get a whole list of instances that it belongs to, or classes that it belongs to. So for example, for data bool, which has the two data constructors false and true, bool is an instance of the equality class, right? That means true is equal to true, false is equal to false. Bool is an instance of the ordered class. That means false is less than true. True is an instance of the enumerable class. That means the true false is in one-to-one correspondence with the natural numbers. That is to say, something comes after false and something comes before true. Boolean is showable. That is, there is a text representation. When I ask REPL to print true, it prints true. It's readable. That is to say that there is some type of parse that I can do on true and false to get back true and false. Which one's easier, show or read? Did you say read? Okay, that's better than read. Show is much, well, what is required to read something? Like if I asked you, you can pick one of two projects, print this Python code or interpret it. Which one do you want? Which print? Okay, so show is way easier than read. Read will require parsing. So we're going to return to that class as like the very last thing that we do. And finally, a bool is an instance of the bounded class. Like one of its two elements is the largest. Once I asked a bad exam question because I assumed that bounded implied order. That's not the case. There are such things as partial orderings, right? So bounded just means you have a largest element, but I found that kind of peculiar. So class constraints are a way of restricting an abstract type to a certain class, right? So because there are many things that can be numbers, I still want to have the capacity to say, oh, the type here is A. It just has to be an A that has this sort of class constraint. And we can, we sort of enforce these constraints by writing it like this. So if C is a class, and A is abstract type. And by saying this, you're saying that A, the abstract type, is constrained to the type class C, right? So something like, I demand A is an instance of this class. And once that's the case, then you're a function that goes from A to A, right? So to the left of this sort of inference symbol is the class constraints, and to the right is just sort of the function definition. You can have multiple constraints. You could just pack them into a tuple like this, and I can say constraint 0, constraint 1. I don't know why there's not a constraint 2, but here's a constraint 2 that's named constraint 3. So you can have multiple ones. So a type with one or more class constraints is called overloaded. And this is a weird name to be overloaded. So something that I want everyone to realize now is that the less constraints on our type, the less functions we can define. The more constraints on our type, the more functions we can define. This seems weird. It seems like constraint means less. Let's think about this. How many functions are there from the abstract type A to A? Give me one function. Identity function. Give me one more. That's it. That's it. One function we can define over the abstract type A to A. Let's put one class constraint on it. It's an integer. How many functions now? Infinitely many. I have constant to 1, constant to 2, constant to 3. And so this is bizarre, right? We need constraints in order to define anything. Okay, so most of our functions are going to be overloaded because there are not many not overloaded functions. One of the true challenges in this class is to actually ask new questions because there's so few super patterns at the top. And that's what you'll see we'll keep doing in this class, is like sort of removing constraints and coming up with these super patterns. So here are the basic classes, right? So the equality class says you need to define equal and non-equal. And obviously, once you get one, you sort of for free get the other. I'm not saying these things have to be independently defined. Like mutual recursion is something that we're going to be totally fine with in this class. To be ordered, you have to define the following things: less than equal, greater than equal, min and max with those types. To be showable, you just need to take A and return a string, right? So to show false is false. To show this is 1, 2, 3, right? Because both of those things were from a showable type class. We can read. So I can read false. This is a little bit tricky. For what is read a safe function in Haskell? No, right? So this is fine. I'm saying read false as a Boolean, right? That typecast is going to be necessary. Otherwise, it doesn't know what to read into. Can I read this as an integer list? Yep. And this is also kind of interesting. The more typical way we see reading is not by typecasting, but by simply using it. So the benefit of the type inference engine is I can say, read this as false and not it. And Haskell goes, oh, user's nodding it. This should be read as a bool. Isn't that great? Isn't type inference awesome for that reason? That's cool. Okay. So this is a partial function. We're generally trying to stay away from using partial functions. This is Haskell will read this. This is fine to Haskell. It's saying read is a function that takes strings to types. This is a string. This is a type. Language rules satisfied. Typing satisfied. But as soon as Haskell tries to actually find the integer that is equivalent to the string false, it can't find it. And then you get an exception, which are, I think exceptions are sort of worse than typing errors. Typing errors you can go and fix. This won't happen until you've deployed the code and someone's triggered it. That's bad. That's worse. Okay. Exceptions are worse than typing errors. The numeric class contains these types. So you need to define addition and subtraction and multiplication and negate and absolute value and signum, which is just a special function which tells you if a number is positive, negative, or 0. So it returns plus or minus 1 or 0. For those of you from math should be sort of quite familiar with sort of like this numbered class. This effectively is like a group, right? So like the analogy here is like, oh, math says, oh, if you have a set that like has an additive closed, that has an addition on it that's closed, that satisfies a bunch of other properties, then you're called the group. If you also have multiplication, then you're called the ring. Like this is very similar to us saying, oh, if you want to be a number, then you have to provide the following functionality, like a closed addition operator and so on and so forth. There's an integral domain. So the integral class is a subset of numbers, but in addition to the things that numbers provide, you also have to get integer divide and modulo. Fractional is a little bit different, that you get sort of this fraction operator and reciprocation. Here's enumeration, right? So enumerable types are important because these are effectively the things we're going to be able to loop through. So can you enumerate through the rational numbers? Fractions? You can enumerate through fractions. Just put them on a grid and do this. You can walk through them. Can you enumerate the reals? No. Okay. So like there's some things that are going to be enumerable or countable and other things that aren't. The relevant thing in this instance is that we have the successor and predecessor function, right? Once you get successor and predecessor, you get the rest. And you don't actually need to define all of these, right? If you look here, whoops, what was the class? Capital. It says down here, minimally. Like this is the thing that I want you to define. We need all of those things. But actually, if you just define this one thing, I can deduce the rest. Okay, so you can either provide them or not provide. You'll see the same thing. Perhaps this will be easier to understand for the equality class. It's saying minimally you have to define equal or not equal. It's able to deduce the other one naturally, right? So often it's the case that you get a bunch of free functionality just by the nature of how some of these things work. Okay, so we're going to create our own custom type, and then we're going to make that type part of a class. We're going to do it. Okay, so this is the most typical usage case for new data, days of the week. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Those are the symbols that I want to be included in my day type. Okay, is Monday less than Tuesday? I haven't told Haskell anything about this type. Is Monday equal to Monday? Nope. Is Monday showable? Nothing. Okay, so out of the box, what do we have? What can I do on this type?
Values.
If I gave you a list of day, could you count the number of times Monday was in it? Yes, because what is the one thing all data provides out of box? Pattern matching. I can detect Monday, right? Right, so I'll just put this data into here. Okay, and I can have foo, and I can already say foo of Monday is 1. Okay, let's just load that in. Foo of Monday is 1. Also notice no quotes. This isn't strings. This is properly new literals in the system. Okay, so I don't have foo Tuesday. I haven't told it anything about that yet, but we do have pattern matching, which means I can count stuff. Not by using the equality operator, but by doing pattern matches. Okay, so that's important. Where we can do pattern matches, you should do pattern matches. Okay, so in order now to say that I'm going to insert this into the show class, I'm going to make day an instance of show. All I have to do is minimally define a show function. And here it is. To show Monday, type Monday. To show Tuesday, type Tuesday. So now we do have these like strings around. So once I define this, then Haskell knows if I type in Monday to print Monday, to do Tuesday to print Tuesday. Okay, so this is the most obvious way of showing this data, right? What about equality? Well, here's the most obvious way of defining equality. Monday is equal to Monday, Tuesday is equal to Tuesday, Wednesday is equal to Wednesday, and so forth. And if you get to this line 9, false. Because everything that was equal to one another should have been equal to one another. I said there are limited places in Haskell where ordering matters. And defining these guards, or like the order you declare this in matters, right? Because if I put line 9 at line 2, does Monday satisfy this pattern? Like this pattern says, give me anything in the first position and anything in the second position, I'm going to return false. If I move line 9 to line 2, it gets everything would be going to false. So we have to maintain ordering here because Haskell's going to say, I'm going to check this pattern first, and then this one, and then this one. Right, so ordering there does matter. So at this point, I can't say Monday is equal to Monday, and Monday is equal to Tuesday, and it's going to say false because it went all the way down to here. It couldn't find that pattern. Okay, so type class instances we can derive. Okay, so what's obvious here and here? Look, we just did something incredibly obvious, right? And it's sort of like, man, this would have sucked if the data type was infinite. Like, how was I supposed to do this? Or if there was a lot of data. So we can just instruct Haskell to do the obvious thing in those cases. If I say derive show, it says, oh, okay, I'll just, whatever the literal is, I'm just going to print that. That's what I'm going to do as show. It's the obvious thing to do. We can hard code it, but Haskell can handle that for us. Same thing for equality. It's like, oh, okay, well, let's just assume that like every piece of data is equivalent to itself. It's another sensible thing to do. That's another thing that can be automated away. So Monday, we'll now print Monday. Monday is equal to Monday is true. Monday is less than Tuesday. Do we have this? No. Okay, but do you believe that this is one of the ones that we could automate? Do you think we could derive less than or derive order? What is the obvious thing Haskell will do in this case then? It will say Monday's less than Tuesday, Tuesday's less than Wednesday. It will just utilize the natural order I wrote this. Now, if I permuted it, it wouldn't make any sense, but it will use it nonetheless. Can I derive number class from this? Well, what will the closed addition operator be? What will the absolute value of Thursday be? Well, the point I'm trying to say is that now that you're saying so many things that it has to reason out, no, it won't be able to. There's no super obvious way of turning a collection of random literals into an additive group, right? So there we go. So some of them will be derivable and others won't. And the ones that are derivable like should have the sort of obvious derivations. Okay, so what I want to do now in just maybe the last 10 minutes is just review induction. Because every year, everyone claims they know this super well. And then I give a geometric problem to solve and everyone sort of gets confused. Because they're saying this isn't the 1061 style of induction. And that statement makes me want to tear out my hair. Every year I get a little bit more bald hearing that statement. There's no such thing as 1061 style induction. There's just induction. Okay, induction. And this is induction that I've written up here. So, okay, before we get into induction, were there any questions about type classes? So just to reiterate, like, you can have a type, and a type can belong to a class, provided that it defines a bunch of functionality that that class demands. And then you can occasionally derive this for free. Yes, sir. Yes. Because all that's required of you is to define those things. And the other thing I didn't mention is it doesn't have to be mathematically sensible, right? Like nothing's enforcing actual group rules on any of these things. You can come up with totally nonsense operators as long as they exist and are typed properly. Like you can write a show function that takes everything to empty string. Wouldn't be very useful, but it would type properly. And Haskell would be totally fine with that. Probably, yeah, show should have the property that you can read what you show back into the data type, right? So we would put rules on over it. So that's why I'm teaching you both math and Haskell at the same time, because we need both in order to work with this system. Yeah. Anything else? Okay, so the point of induction, you have some type of predicate. That predicate is encoding a statement from the natural numbers into the Booleans. That is to say, like, P of 0 is either true or false. P of 1 is either true and false. P of 2 is either true and false. And the thing that you want to demonstrate is that P is true at every single integer. So that this begs the question then, how can I prove something is true an infinite number of times? And the method for doing this is that of induction. And I'm just going to try to work out, like there's a core misunderstanding here that I want to try to like just sort of get rid of. Right? Because induction and recursion are effectively the same thing. That's what I need you to understand. The induction question I gave you on your first assessment, I'm asking you to write that precisely because on assignment 2, you're going to write the algorithm that implements it. So assignment 2, I'm going to say, write me a Haskell program that's going to conduct the tiling for an arbitrary size board. Right? So that's why your induction needs to be precise enough that someone is able to take it and write a program based on it. So just keep that in mind. That's ultimately the objective. Okay, so you have some type of predicate P. We want to assert that P is true an infinite number of times. If you can establish these two things, then you have done so. If it is the case that PM is true, then PM plus 1 is true. If you can show that inference is true, and you can show that P naught is true, then you've shown everything is true. Okay, so this is the sort of English statement. This is the logical statement. This is the principle of mathematical induction. Give me some function P that goes from the naturals into the Booleans. If it is the case that P naught is true, and for every M that's a natural number, the truth of PM implies the truth of PM plus 1, then it is the case that P is true at every M. And this is the huge hangup. This is why I think undergraduate students get confused about induction. Induction proofs contain the bizarre statement, assume that Pn is true. And then people scratch their head and they say, isn't this what we're trying to prove? No. Okay. We need to demonstrate this inference statement. Okay, so this is something like A implies B. In order to, what is the first step in proving A implies B? Suppose A. So this induction hypothesis is that assumption. I'm saying I need to prove this inference statement. So I'm going to assume the antecedent of this inference statement and deduce this. So we are not assuming for every NPN. I'm saying pick an N. I am going to then assume that Pn is true and show that it follows that Pn plus 1 is true. That is so different than assuming the thing that we're trying to prove. Because if I give you an infinite chain of statements that need to be true, how can we assert that everything is true? Well, if we can say that if the 7th member is true, then the 8th member is true. And that is true at any insertion point. Like, oh, here, I know that if n is true, then n plus 1 is true at an arbitrary part of that logical chain. And I know that the first thing is true. Then what happens? Well, if the first thing is true and I have a rule that gets you from 0 to 1, then 1 is true. Well, if 1 is true and I have a rule that gets you from 1 to 2, then 2 is true. And then this chains. And then you get the truth of the proposition for any fixed n. Okay, so that I think is the hang-up. We are not assuming Pn is true for all n. That would be genuinely the thing that we're trying to prove. I am assuming the antecedent of an inference statement in order to prove the inference statement. I am assuming A in order to establish A implies B. Okay? So here's the prototypical example for induction. And I think the problem in 1061 is that they show you this, and then they give you a bunch of other arithmetic statements for which to do induction on. And then everyone escapes that believing that induction is only useful for like working out identity equations. Because I often get the question, because the question I gave you is geometric. There is like no equation. Every year, someone is going to prove the number of tiles is divisible by 3. Every year, right? Because someone is going to try to induce an arithmetic statement on that geometric problem. Right? And it's not. We need to understand induction as sort of a larger principle at play. So I'm going to demonstrate it on this, and then we're going to move to a geometric problem. Right? So I'm going to utilize this as an example to tell you how to maximize your homework score. Right? Because the induction is somehow a good place to get marks. Because I'm just looking for things to exist, right? Before they necessarily have to be correct. Okay. Step 1 of your induction proof is what? State the thing you're proving. What is your P? This is the most important part of the whole proof. Step 1, codify the statement that you're trying to prove. So you should have some statement in your homework like Pn is this condition about your board. Not some arithmetic statement. So in this case, the proposition Pn, the thing that is going to be true or false, is the assertion that this identity is correct. Pn isn't equal to anything. It is logically equivalent to something being true. If I see, like, it would be inappropriate to say Pn is equal to nn plus 1 over 2. Okay, it has to be something that evaluates to true or false. It needs to be clear. Okay, so step 1, state P, free mark. Some of you may not do it, but please do it. It's the most critically important part of the whole proof, in my opinion. Next step, base case. Your base case has to be the right base case. The other thing that we're going to have to get over is this, I don't know, what's the Gen Z term? Ick? This icky feeling we have with vacuous cases. So what is the empty, what does it mean to sum 0 numbers together? It's 0 definitionally. Okay, so here I'm just saying, well, the 0 sum is definitionally 0, and 0 is equal to 0 true. If you don't go deep enough in your base case, we're gonna take the mark away. If you started at 1, you've now missed 0. You have to include every natural number, right? Some people would choose 1 just because it makes more sense to say like 1 is equal to 1. What is the minimum example for your tiling example? How many tiles does it take to tile nothing? 0 tiles. The absence of tiling is still a tiling. It's trivial. If your base case isn't trivial, your proposition's wrong. Your base case should be free. And why do we want it to look like this? Because we're programmers and we're lazy. Like, I want my base case to be the easiest thing to program. I want to say sum of empty list is 0. I don't want to do any work in the base case. Okay, so there's my base case. Inductive hypothesis. I'm going to do the strange thing now, right? I'm going to assume that Pn is true, but only in this inference chain. You must state an induction hypothesis somewhere. Everything pink here, check mark, check mark, check mark. And the absence of it is the opposite of a check mark. Induction. Now I'm going to show that because I assumed Pn is true, that as a consequence, Pn plus 1 is true. And this is easy, right? So I'm just saying, okay, here's Pn plus 1. That's what you start with. This is logically equivalent to this statement. By definition, that's what we wrote. That's how we defined P. Oh, but I can, this can actually be rewritten like this. And the thing I have in magenta is actually Pn, which is our induction hypothesis. So our induction hypothesis says that this is fairly replaced by this. And after some arithmetic, you can show that this is equal to true. Right? You've all seen this maybe 100 times. Okay, and then conclude. And you do have to invoke the principle of mathematical induction because you're using a theorem in order to assert the truth of your proposition. Right? So you have to say, by the principle of mathematical induction, I have done the requisite things, and therefore I've proven the thing that I've wanted to prove. Okay. Let's do a geometric one now, and you tell me how we're going to codify everything. Are you familiar with this problem? Why are we groaning? I love this problem. I'm going to write a two-line Haskell program next week that solves this. I can do quicksort in 1 line in Haskell. Okay? Not long. Okay, this is okay. So if we think about this the right way, the program is going to be easy to write. 10 units of thinking in this course, 1 unit of programming. That may be the inversion of what we're used to doing, but there's no such thing as hack and slash programming in Haskell. It won't work. You can't write a partially complete Haskell program. It just that doesn't even mean anything. Okay? So we have to think quite hard up until a point where programming it will be trivial. Okay, so I'll just state the problem. This is a game. There's 2 rules to this game. You can only move 1 disk at a time from one peg to another. And no larger disk can go over a smaller disk. Did everyone understand that? Prove that you can move this tower from the left peg to the right peg for an arbitrary number of disks. Because I know for 5, you can just demonstrate it. But what would you do if I said, well, but for any amount of disks? Okay, so we just go through induction and it solves itself. And this is recursion. So I'm going to teach you how basically if you just think inductively, problems are going to magically solve themselves just by the nature of the paradigm. What should our proposition be? Yes, miss. No. For one, it doesn't have an in it. You're close, but we have to, since this is so critically important, we have to make a very precise statement. Here's my precise statement. Pn is equivalent to the following being true. A stack of n disks can be moved to I'm going to say arbitrary pole. I'll make it a little bit easier. While moving 1 disk at a time, bigger disks are never stacked on smaller disks. Is this a precise statement? Does it use a bunch of symbols? Okay, so when I say precision, I don't mean use a bunch of symbols. I mean, the thing that you say should have exactly one meaning. Yes, sir. Well, I guess because there's a picture, there's like context as well, but fair. I could include that if, yeah, that was confusing. But use pictures too. You're allowed to use pictures. If you all took graph theory, you'd understand that like sometimes we have to use pictures to describe things. Is it so everyone clear about what the proposition is stating? What's P0 say? Can you move 0 disks from pole 1 to any other pole? Yep. Yep. How would this look like in your programming? You would return empty list, an empty list of moves. And that's what you want to return. That's easy. That would be an easy base case. Okay. What's now our induction hypothesis? Well, we assume Pn, but that means we assume that I can move n disks from any pole to any other pole. Okay. Can we then use that to solve this problem? Okay. So I'm assuming n. I can move n disks. right? While not violating any of the rules. So there are 1, 2, 3, 4, 5 disks here. Suppose I can move 4 of the disks as a tower. How can I solve this problem? Move the 4 to the middle, move that there, move 4 back. Proved. We're done. Implement that and it will work. But how do you move 4 disks? Well, move 3. Well, how do you move the 3? We'll move 2. Well, how do you move the 2? We'll move 1. Well, how do you move the 1? Well, none. That's easy. That's induction. So that statement I just gave is sufficient to actually now go program a recursive algorithm to solve this. You just have to give some thought about how to encode it. So next class, we'll do that together. Yeah. Yeah.
Continues with the picture. Is that sort of what you're asking us to do?
Well, I'm saying Pn is like something here that's defined. It's logically equivalent to something, right? So when I'm saying P0 has to make, to assert P0 means I have to logically make it equivalent to true. Oh, well, because I'm speaking out loud, you'd have to write that, right? I'm not saying this comprises like a perfect written proof. Okay. See you next class. Welcome back, everyone. Come see me if you have any problems. Try to program this.